Why does a spacecraft returning to Earth glow like a meteor, hot enough to melt metal, when it's not even touching much air up there? Here's the real reason. Reentry gets hot mostly because the air in front of the vehicle gets compressed violently, and compressed gas heats up fast. It's like a bicycle pump, push hard, and the pump warms in your hand. Now imagine pushing the atmosphere at several kilometers per second. A spacecraft in low Earth orbit is moving insanely fast, around 7 to 8 kilometers per second. That speed is stored energy. On the way down, that energy has to go somewhere. You can't cheat physics. If you slow down, the energy turns into heat, mostly in the air, and then into the vehicle. As the craft dives into thicker air, it can't politely move the air out of the way. It slams into it faster than the air can flow around. So the air piles up and forms a bow shock, a compressed shock layer right in front of the heat shield. Near the very front, called the stagnation point, the airflow is forced to nearly stop. When gas is compressed that hard, its temperature skyrockets. Molecules start vibrating more, collisions explode in frequency, and the shock layer becomes a furnace. People say reentry heat comes from friction, like rubbing your hands together. That's a trash explanation. Yes, there's drag, and yes, there's shear in the boundary layer, but the dominant heating is not skin-rubbing air. The big heat source is the air being crushed and shocked in front of the craft, kinetic energy turning into thermal energy inside that shock layer. The craft is basically a moving piston compressing the atmosphere. So how does that heat actually get into the spacecraft? Two main ways. First is convection. Superhot gas flows along the surface and transfers heat like a blowtorch. Second is radiation. When the shock layer gets hot enough, it emits light and infrared like a glowing stove coil, and that energy radiates toward the surface. At very high speeds, like lunar return or interplanetary entries, radiative heating can matter a lot more. Here's the clever trick. Most crew capsules are blunt, not sharp. A sharp nose can keep the shock wave attached right on the surface, dumping heat directly into the material. A blunt heat shield pushes the bow shock away from the vehicle, creating a standoff gap. That gap helps keep the hottest gas a little farther from the surface, reducing peak heating. It's counterintuitive. Blunt looks draggy, but drag is exactly what you want when you're trying to slow down safely. Then comes protection. Some vehicles use ablative heat shields, materials designed to char, crack, and slowly erode. That sounds bad, but it's genius. As the surface material breaks down, it carries heat away and forms a protective gas layer that insulates what's underneath. Other vehicles, like the Space Shuttle, use ceramic tiles that don't melt easily and are great insulators, keeping heat from reaching the structure. Different mission, different design trade, reusability, maintenance, entry speed, and safety margins. And that glowing trail. That's often a plasma sheath, air heated so much that electrons get knocked loose. Plasma can absorb or reflect radio signals, which is why some spacecraft experience a short communication blackout during the hottest phase of reentry. So reentry heat isn't mainly rubbing. It's the atmosphere getting compressed and shocked into a superhot layer, then blasting the vehicle with convection and radiation, while the heat shield either insulates or sacrifices itself to keep the crew safe. Now I want to hear your guess. If you could redesign reentry from scratch, would you choose a tougher heat shield or a smarter trajectory that reduces heating in the first place?